Hi, Tai-Danae. We are back together again for another FAQ conversation where we talk about what's actually happening inside a trapped ion quantum computer using DiVincenzo's criteria as a guide. And I got to tell you, Tai-Danae, I am extra happy and excited to have this particular conversation with you today.
Oh, okay. I'm excited too. Why are you excited?
Well, I think I can start by talking a little bit about like a recap from our last
Yeah.
couple of times, and I think that kind of gets into my excitement. But to not
Yeah.
bury the lead, I'm excited because I know very little about what we're going to be talking about
hmm
today,
hmm
and I'm always extra motivated to learn new things. And you're such a great teacher, so just like how I
Oh,
learned a lot last time, I'm looking forward to learning a lot this time. No pressure on
yeah.
you there. So yeah, but I'm looking forward to the conversation. So to kind of remember, it's been a little while, so to remember what we were
hmm
talking about last time, we were looking at DiVincenzo's criteria number 3 and number 4. And as a reminder, DiVincenzo's criteria number 3 is about long relevant decoherence times, or
hmm
essentially at least decoherence times that are longer than gate operation times.
hmm
And DiVincenzo criteria number 4 is about a universal set of quantum gates. And that's where we spent a lot of our time last time talking about single qubit gates and superposition. And that's where you kind of blew my mind a little bit when you showed me that graphical representation of what superposition really
Yeah.
is mathematically, but then how you can physically use lasers to get qubits into
Yes.
superposition and affect their probabilistic state. So I'm
Yes.
kind of hoping that this time, I know we're going to be talking kind of this is kind of a part two actually of that conversation because we're going to continue talking about decoherence times a little bit, but I know we're talking more about gates, and instead of single qubit gates like last time, we're going to be talking about two qubit gates this
Yes.
time. And that has something to do with entanglement, which is another one of these things that has been a little difficult for me to kind of wrap my mind around as I'm learning about quantum computing and about quantum physics in general. So I'm hoping that you'll be able to kind of give me a little bit of that aha moment that you gave me last time with superposition, but to do it this time with entanglement. So that's why I'm really looking forward to this one.
Okay. Excellent. That's a helpful recap, and I'm looking forward to this too. Before we get started, maybe I want to say one thing.
Sure.
If like entanglement, obviously, is a word that you find quite often online if you just kind of poke around for quantum computing and so forth and so on. And a lot of times it has this adjective in front of it, like spooky or weird or counterintuitive or something. And
Mm-hmm.
it's true that, and even we've had on this podcast in season one, you can have philosophical discussions about entanglement, and there's a lot there. But just to not bury the lead, as you said, in this conversation today, what we would like to do is to discuss entanglement from a very concrete, like what are you actually, like what's actually going on with a calcium ion and with these lasers that you're shooting at it. So if I would say, you and I have talked about like the philosophy and stuff before, but let's pretend we've never heard the word entanglement. I know that it's a little bit difficult, but like let's empty our brains of any preconceived notions or opinions or whatever about this thing, and let's just come in with an open mind. And I think that will be helpful in understanding what it really is, at least from a concrete point of view. How does that sound?
That sounds great. And I think it's going to be probably easier for me to like purge my memory
Yeah,
of
purge.
what I know about entanglement than for you maybe. But I'm pretty new to all of this. So I think that's great. And yeah, I'm always a big proponent of kind of trying to demystify things and removing
Yes.
those barriers of like, if you say that it's spooky and difficult
Yeah.
and counterintuitive and hard to grasp before you even start, then you're kind of
Yeah.
like not setting your brain up for success in being able
Exactly.
to absorb the new information. So I'll try to like wipe all that out, start with a clean slate, and looking forward to the entanglement discussion and what that has to do with what's happening with those calcium ions inside a trapped ion quantum computer.
Yes. Yes. Fantastic. Okay. Let us set ourselves up for success. And let's start. I want to actually bring up the graph that you mentioned. So you mentioned that last time we talked about superposition and we saw
Mhm.
this nice sort of sine squared looking graph that we borrowed from the Penny Lane article. And just maybe as a quick recap, remember you have your calcium ion and there's this sort of valence electron, and it can either be in a ground state or in an excited state. And we said, how do you know? This is kind of getting at the final DiVincenzo's criteria, but to kind of give that away, you shine a laser on it. And in this setting, if the ion fluoresces, if you see it sort of shine a little bit, then oh, my ion was in the ground, it's in the ground state. If it does not fluoresce, if you don't see a little beam of, ball of light, then it was in the excited state. And we talked about that last time. And the whole idea behind this graph is that you're going to see fluoresce or not fluoresce with a certain probability. And you can adjust that probability by adjusting the duration of your laser pulse. And that's what this graph is showing. So on the x-axis is time, and on the y-axis is the probability of seeing your ion not fluoresce or seeing it in the excited state. And so that was kind of us demystifying superposition. Oh, if it's, in a 50-50 superposition, that means I've tuned my laser to, pulse for a certain time duration. If I do this 100 times, 50 of the 100 times I'll see it fluoresce ground state. The remaining 50 I'll see it not fluoresce excited state. So I just want to say that as kind of a refresher. And we use this notation. Do you remember this kind of ket, ground, ket, excited, G and E? Last time we used zeros and ones, but today let's just think of 0 as like the ground state and 1 is like the excited state, and we'll use the letters G and E. Does that kind of ring a bell?
Totally rings a bell. Sounds good.
Basically, there's a number associated to the ground state and a number associated to the excited state. And you want them to have the property that when you square them or do the complex analog of that, they get 1. So the squares are the probabilities. Now,
right.
If you can see here, I've written 1 over square root of 2. That's the number associated to ground. And that's just because if you multiply 1 over root 2 by itself, you get a half. So that's just an example. I'm writing down mathematically what I just described in English, this setting of, okay, suppose I shine my laser for the amount of time prescribed by the graph. Then if I measure this ion 100 times, half of the times I'll see it fluoresce and the other half I won't. Mathematically, you can express that as this sum right here. But, that's just for those who want to think in terms of the math.
Great.
Okay, now that was we just recapped the 1-qubit gate, or how you can adjust the state of a single ion using lasers. Now, let us move the conversation to 2 ions. Imagine, Adam, I have 2 calcium ions right here, this one and this one. I'm going to describe an example of a 2-qubit gate. It's super simple. Imagine you have 2 lasers of the kind we just finished discussing. I can shine the first laser on the first ion for a certain amount of time and put it in a particular superposition, a la the graph. And I can do the same thing on the second ion. Maybe I shine it for a little bit longer or a little bit shorter, but I'm just applying that idea we just talked about on 2 ions. Does that make sense? Like, that's the thing I can do.
Totally
Right.
makes sense. And one thing that might be useful to chat about around this time, or maybe even earlier in this conversation, is we talked about 1-qubit gates. Now you're going to talk about 2-qubit gates. We're not going to talk about 3-qubit gates and 4-qubit gates, right?
No, that's not my plan.
Because I think right, okay, good. Because I think I remember from our last conversation that there's some mathematical proofs or stipulations or something you were talking about, that if you can do 1-qubit gates and 2-qubit gates, you can do everything that you would want to do with a much larger number of qubits. Am I remembering that correctly?
Yes, that's correct. So there's a nice result that says any operation you want to perform on a collection of qubits, you can basically do that operation by operating on the qubits 1 and 2 at a time, kind of like, building this nice structure out of Lego pieces that have 1 or 2 little nodes or something in them. That's kind of the idea. Exactly right, what you said.
Gotcha. Great, thanks.
Yeah. So I'm just giving an example of how you can operate on 2 qubits at a time. You can shine a laser on one and a laser on the other.
Makes sense.
Okay, I don't know. There's nothing to say there. That's really easy. So suppose now, so look, here's how I kind of envision it. I have my first ion or qubit. I'm going to use the word ion. I'm just going to call it A, and I'll call my second ion B. because I just want to distinguish them. Now, imagine we do what we did before. Suppose we shine a laser on A tuned at the right frequency and for the right amount of time such that on the graph, my superposition is in that 50-50 split. So in other words, I'm going to shine my laser on A long enough so that if I measure it 100 times, 50 of the times I'll see it fluoresce and 50 I won't.
So you're just getting it into superposition.
Just getting it into superposition, the one that we just talked about. Now I'm going to do the same. Now I did that with A. So here's A, it's in its superposition. Good job, A. So while A is over there, I'm going to come over to B and do the exact same recipe on B. I'm going to shine my laser on B for the same amount of time so that it's also in a 50-50 superposition, right? So here's A and here's B. Great. Now, to kind of verify this, like I set this up and we checked our math, the same math from last time, so that's how we know that this graph coincides with reality. So let's just say what that means. Here I have my two ions, A and B. Each of them are in superposition, the kind we just described. What does that mean? As it stands right now, there's a 50% chance that A will be in ground or excited, and there's a 50% chance that B will be in ground or excited. So let's just test this out. I'm going to measure one of these ions. Let's say I pick A first, right? So if I measure A, if I shine a light on it 100 times, 50 of those times it'll be ground, 50 of those times it'll be excited. No big deal.
You're talking about like you'll only shine it once per like superposition state. Right?
Yes. Oh my goodness. Thank you. So if I put in the superposition state, I measure it, I find it in ground. I like put, a tally mark on my sheet of ground versus excited. Then I put it in superposition again. Thank you. And then I measure it again and maybe this time I got excited. So I'm now going to put a tally mark in excited. And I do that 100 times. Yes. So I'll have 50 tally marks in ground and 50 on excited.
Okay.
And then I go over and I do that to B and I find the same thing. That's what it means for both of these to kind of individually be in this superposition state. This is like straightforward, and if you're like, but where's the catch? There is no catch. I'm just sort of saying, hey, that thing that we talked about last time, just do that on two different ions. That's actually an example of a two-qubit gate. I transform the state of two qubits by acting on them individually. But that's an example. It's kind of a simple example, but that's an example of a two-qubit gate. How's that so far?
Great.
It's great. Okay.
Yeah.
Let me now describe another example. Okay. So for those who are interested in the math, the superposition state, just recall, of the first ion, I can write it as 1 over root 2 times ground plus 1 over root 2 times excited. In other words, 1 over root 2 is that number such that I square it, I get a half or 50. That's just kind of the mathematical representation of that scenario we described in English. Now what I want to do is show you another mathematical setup of these two ions, A and B. I'm just going to show the math, but then let me actually describe what's happening in English just like we did with this. But I'm going to put the math up front just for those who are interested. Okay, so here it is. I've written 1 over root 2 times excited and ground plus ground and excited. Okay, what does that mean? Don't worry about the math for now, but just think this is a state of two ions, and it's different than the one I just described. And let me tell you what it is. And let's think about how it's different than the one we just described, okay? So this is a setup that goes the following way. I have two ions, and they're in the following situation. Just as before, both ion A and B have a 50% chance of being found in ground or excited. So the initial kind of setup looks the same. Mm-hmm. In this scenario, though, let's say I measure A, and I want to see, is it going to fluoresce or not fluoresce, okay? And let's say I shine it, it's ground, I put a tally mark on ground. I shine it, it's excited, I put a tally mark on excited. If I do that 100 times, A still has the property that I'll have 50 tally marks on the ground part and 50 tally marks on the excited part. But here's the interesting thing. If I shine a laser on A and I get excited, I then want to see what B is going to be doing. Previously, B can do whatever. It could also be ground or excited. But it turns out in this case, in this scenario, if I measure A and I find it to be excited, then I shine a laser on B, I'm always going to find it to be in the ground state. So if A fluoresces, then I measure B, B will not fluoresce.
Okay.
Does that make, okay, so let's say I do it again.
Mm-hmm.
I do it again. I measure A, I shine a light on A, it is in the excited state. I think excited actually means not fluoresce. Anyway, I shine a light on A, it's in the excited. I do that 50 times. I do that, let's say 100 times. 50 of those times I get excited. For each of those 50 times that I get it I see that it's in the excited state, meaning it doesn't fluoresce. For each of those 50 times, when I measure B, B will always do the opposite, fluoresce.
I mean, that sounds really cool and interesting, but they seem like they're connected, which is another word for entangled. Yeah. So I think that's where we're going.
Yeah.
But the situation makes a lot of sense to me, but how that actually works, I have no idea.
Okay, fantastic. So this is what we want to spend the rest of the discussion on. How do you take two ions and put them in this scenario? Okay, so you're exactly right. This is an example, that kind of correlation, like if A does this, then B is going to always behave in this way, whereas before B could do whatever it wants and A could do whatever it wants, but now they're kind of related. This is an example of two ions being in an entangled state. So this is what entanglement means, just concretely in terms of the superposition and all of that. Okay.
Great, that makes sense.
Okay, good, fantastic. So now let's spend the rest of the conversation describing how do you take two calcium ions, suppose, to go back to, I forget which episode it was, 2 maybe of this season. Suppose they're initialized. So we talked about initializing qubits, right? So suppose I have two ions. They're both in the ground state, meaning guaranteed 100% of the time, both of them are going to fluoresce. We've initialized them ground. Well, okay, we've initialized them. How do you shoot lasers at these two calcium ions such that when you go to measure them, you get this other scenario that we just described what's really called entangled. So that's what we're going to talk about now. This, I think, is super interesting. Let me first, can I give the short version for those who are I just wanted to go dive into the philosophy now, and I don't care about how it's implemented. And then I'll give the long version for those who are interested. So do I have permission to give a short version?
Absolutely. Yeah. Bottom line it.
Bottom line it. Okay. I like to think of it kind of I have a couple of analogies. I'm going to use the following analogy. Imagine, Adam, like a treasure map, okay? And the starting point of your treasure map is two ions both in a ground state. The sort of X marks the spot, or, finish line of your treasure map is this entangled state. And we wrote the math expression earlier, okay? And so somehow we want to go from the starting point, ground state, to this entangled state. Now in this treasure hunt, imagine that there are certain rules that you can abide by. And the only way you can get from start to finish is by following the rules of the game, so to speak. So it turns out when you kind of look under the hood of the physics and the mathematics tells you what rules to follow. And just by following those rules, you kind of hit your two ions with lasers in a certain succession. It's almost like playing a video game, and you're hitting your controllers in a certain sequence, and you get a result at the end. So by following these sort of rules, or this sort of, game analogy, you're allowed to get from starting point to finishing point. that's kind of the big picture of it. And you can imagine, based on our conversation last time, those rules are a little bit mathematical. We saw some of the mathematics last time, and I'm just mentioning that so people know that it's not like some hocus pocus stuff. This is very concrete and grounded in like trigonometry and some linear algebra and things you can really touch and feel, so to speak, with, you know, a pencil in your hand or something. So that's kind of the short version.
Okay. No, I like that. And I think that, yeah, so I think last time we were talking about superposition and the number of pulses and the wavelength of lasers that you need to use in order to get the certain probability that you want within superposition. What I'm hearing from you is that similarly, you can do that to entangle qubits. It's just a little bit more complicated, maybe slightly different wavelengths or different times. And I really like the analogy as like a child of the 80s of like growing up with Nintendo and stuff. Of like, it's almost like a little cheat code or something where it's like down, up, like A, B, A, B, 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 A, and then you like unlock something. So does that sound about right?
Yeah. Yes. That's great.
Okay.
So that's the short answer for folks who aren't so interested in the details. But now let's like, you know, pull the curtain back a little bit and talk about what that cheat code is.
Great.
So here's the interesting thing. Okay. We have to bring another character into our story. Now, I think you will remember this from several episodes ago. But for quite some time, we have been talking about energy levels of a valence electron associated to a calcium ion, right? Mm-hmm. And, you know, we've talked about how those energy levels are sort of discrete. They can be enumerated, the first level, the second level, the third, and da-da-da-da. But we also said that in a trapped ion quantum computer, you have a chain of ions. So they're not in isolation. They're sort of next to one another in this nice, you know, kind of pearl necklace looking thing. Mm-hmm. And remember this, if I have two ions, both of the same charge, what did we learn in middle school? Two things with the same charge repel each other, right?
Yeah.
Exactly. Yeah. But if I have an ion here, you know, and it's repelling its neighbor, well, it can only go so far until it starts to feel the force from its neighbor on this side. So then it's going to go back in this way and repel. So you can start to see these ions sort of have this vibrational motion because of these Coulomb forces, or these attraction or repulsion forces between them. So this is really interesting. If one wants to understand what's really going on with the chain, not only do you have to deeply understand energy associated to the valence electron, but you also have to understand this motion, how these things are actually moving in space. So this is kind of another thing we have to bring into our toolbox now. Now, the interesting thing, I'm going to actually refer to the Penny Lane article that we know and love that we've been talking about, because I like how they describe it. So, you know, initially the way I'm saying things, you might like, oh, it's like chaos, you know, everybody is doing their own thing. But it turns out when the conditions are set up correctly, the actual chain of ion moves as a whole. It moves as a whole. So it's no longer this person's doing what they want and this person's doing what they... No. All of the ions, if you set them up correctly, start to behave as a unit. So I think I'm going to defer to the experts now. Here's reading from the Penny Lane article. They say, when cooled down, the entire ion chain acts as what's called a quantum harmonic oscillator. So it kind of vibrates. And the interesting thing, what's this quantum harmonic oscillator? Okay, think of it like this. Just like the energy levels of the valence electron are enumerated, we can count them, you know, the first level, the second level, the third level, and so forth. Totally analogously, there are energy levels associated with the vibrational motion of the ion chain. And under certain conditions, the energy levels of the vibrational motion can also be enumerated.
Okay, so like they're also quantized. So that's
they're
like the
also
whole,
quantized. They're also quantized.
Thing.
Yes, exactly.
Okay, so as a way to think about this, so we have the energy gap levels in the valence electrons, like you mentioned. Now we have this like other character, like you said, coming in. So that's kind of, it's just another energy level, but it's capturing like the whole chain or parts of the chain. It's almost
The
like
whole chain.
not an abstraction. Okay, so it's like the energy level of the entire chain
Yes,
is
yes.
sort of another variable or factor in all of this.
Absolutely. Absolutely. Yes, you could say it's another qubit if you want. So in particular, if there are multiple energy levels of the electron, we only pick the first two and we call those 0 and 1 or ground and excited. Similarly, if there are multiple sort of multiple energy levels of the entire vibrational chain, you could just say, hey, let's work with the first two. And so that's another qubit. So that's really interesting. It's kind of like the whole chain also has a qubit associated to it, namely this oscillation. Okay, so we're going to work with that. And sometimes folks call this an auxiliary qubit or sort of like an auxiliary parameter. We're ultimately interested in, does my ion fluoresce or not? Okay, we're ultimately interested in the energy level of the electron. But we're going to use how that one ion sits in this larger chain. We're going to use the motion of the entire chain to sort of transfer information about one ion's energy to another ion's energy. So it's kind of like a conveyor belt. Like you're an ion, I'm an ion, but we're kind of related because we're both moving back and forth in this longer chain. So we're kind of use that like total motion to transfer information about my energy to you. That's actually how entanglement's going to happen. Isn't that cool?
Okay.
This is
That's
neat.
very cool. Yeah.
This is very cool. Yes. Okay. So just to summarize, I do like how they say it. So I'm just going to read here. So they're kind of saying, when we shine laser light on a particular ion in the chain, that entire chain could absorb the energy of the photons and start oscillating, like kind of individually. But when you set things up properly, actually, let me say it this way. If I shine laser on an ion and that laser exactly matches the energy gap between ground and excited, then that single ion is going to bump up from ground to excited, right? That's what we said. You have to tune your laser such that the energy matches the gap from the ground to excited state. But now they're saying, okay, but what happens when the frequency of your laser is away from that value? Like what if the frequency in your laser is a little bit more than the energy gap? Or what if it's a little bit less than the energy gap? So they say in most cases, like that's not going to do anything. But in some special circumstances, it's going to affect or excite both the individual ion and the whole chain. And it's in those special circumstances where entanglement happens. And that's what we want to focus on now. That's really the key.
Okay. So again, another call out for how important it is to have tight laser control. So I know we talked about that last time where it's really important to know exactly what wavelength you're using and exactly for how long you're pulsing.
Yes.
And it sounds like that's just as important with entanglement, if not even more important.
Yes, exactly.
Okay.
So let's proceed to kind of recap. Imagine we are looking at our treasure map. We're starting from the initialized state of two ions. They're both in the ground state. Our goal is to do some laser operations using a cheat code to put these two ions in that entangled state that we described earlier. So mathematically, I'm going to denote the ground state by this ket ground. And I'm going to denote that entangled state that we described earlier by this expression, 1 over root 2 times this thing. I think the math is not, the notation is not as important as long as we remember the concept from earlier.
Okay. And so each one of those, so we're talking about 2 qubits here. So the GG is 2 qubits, both in the ground and okay.
Yes. So the first G represents the first qubit. The first qubit's in ground state. The second G represents the second qubit. And the same thing over here. Whatever letter appears first, think of that as the first qubit, A, I think we called it. And whatever letter appears second, think of that as the second qubit. Okay, so remember, that's the goal. So we're going to spend the next few minutes describing how to go from beginning to end. But to do that, I got to tell you like the controller stuff. You know, I didn't play video games that much, but you know what I mean? Like I have to tell you what rules you can play with, abide by before you can like go punching things in your controller. Okay.
I guess that's one way to go. There's also the way we just like punch and see what happens.
You can just,
but
yeah, just see
I don't
what
think that's how the quantum engineers don't play that game.
No,
I think
they want to be a little more principled than that. Yeah. Okay. So let's describe the rules of the game first, and then we're gonna like use the rules to get from start to finish in our map. Okay. Just so that I don't have to keep holding my hand like this, let us call the energy gap from the ground state to the excited state in a valence electron. Let's call that delta. So that's what delta represents, the amount of energy between ground and excited. Okay, so delta, little triangle. Okay, let's observe something. You kind of have, if I'm going to shine a laser on a single ion, I kind of have three options that I can think about, and I mentioned them earlier. Either I shine a laser whose frequency matches delta exactly, in which case my electron will move from ground to excited, like I've given it exactly enough energy to bump up one, okay? Or I could shine a laser whose frequency is a little more than delta. It's like delta and some change. Okay, so what happens in that scenario? Or I could shine a laser whose frequency matches delta, but a little bit less than that. So it's like this much instead of exactly delta. So what happens? Those are the three things we want to consider. Well, the first scenario actually is straightforward. We just said it. Imagine I have an ion in the ground state. I shine it with a laser whose frequency exactly matches the energy gap. Okay, we said my ion will jump from ground to excited state, right? But remember, we also have this vibrational motion of the whole chain to think about. So like, how did that affect the vibrational motion of the whole chain? In this case, it doesn't do anything. Like you got exactly what you wanted for. It's like going to the store. I want M&Ms. I have exactly much. I don't have to steal from anybody, and I don't get change back. Like it's not affecting anyone. Okay, great. So I guess it will be helpful because I think folks should read the Penny Lane article when they get a chance, but this is called the carrier transition or the carrier frequency. So like maybe not best case scenario, but like the Goldilocks, what's the story with the three bears? Is that Goldilocks?
That's Goldilocks.
Oh, it is. Okay.
Like too hot,
so this
too
is
cold,
like
just right.
Yeah, this is like the just right scenario. Okay. Haven't thought about that for a while. Okay, but what about the porridge? Okay, but what about like when you have too much porridge? What if you have, you shine a laser whose frequency is delta, the energy gap, but also a little bit more than that? Well, the energy that is delta is going to excite your ion, but then there's this leftover. It turns out that leftover energy kind of leaks into the larger chain, and what happens is that it excites the vibrational motion of the chain. So in other words, if your vibrational motion of the entire chain at that moment was in its ground state, like let's call that 0, then when you shine laser with this delta plus extra frequency, your ion excites, and then the leftover energy then changes your qubit of your vibrational motion to 1. It used to be in 0, but now it bumps up to 1. So you've excited both your ion and the whole chain. Okay. So that's option number 2, and that's called a blue sideband transition. I mentioned the name because it'll be just convenient to use that phrase later. So that's option number 2. And then we said what the third option can be. What if instead I shine a laser whose frequency is a little less than delta, a little bit less than the energy gap? So you can imagine writing that as delta minus something, or delta plus a negative number. So in this case, it turns out that if your ion is in the ground state, it still gets excited. So that's the delta. But then you're going to now take away energy from the vibrational motion of the whole chain. So it de-excites the vibrational motion of the whole chain. So if your chain was like in state 1, it'll now go down to 0.
What if it was already in, like, this is starting to make sense, so I'm excited
Yes.
about this. But what if the chain was already at zero and like didn't have any little extra
Yes.
energy to give? What happens then?
Good change. Good question. So in that case, nothing happens. So in other words, the ion just stays where it is and the chain stays where it is. So zero is like the kind of uninteresting thing. But that is important because it's going to come back later.
Okay, so just really quickly, so it kind of
Yes.
seems like that the vibrational energy of the whole chain, this like quantum harmonic oscillator,
Yes.
almost feels like it's a little bit of a energy bank that can be
Yeah.
like used to either like supplement a laser blast that wasn't quite delta to kind of maybe bring it up to delta, but in doing so you're removing energy from the bank from that oscillation.
Right.
Or if you have a little extra than delta when you're shooting that laser at your qubit, you excite the qubit, but you have a little spare change, and then that goes into the oscillator bank and excites the whole harmonic oscillation. Is that about
Yes.
right?
Perfect. Perfect.
Okay.
Brilliant summary. Yes, that is exactly right. Okay, this
Great.
is not so bad, right? I feel like this is like pretty common sense and intuitive. I mean, I don't know if it's common sense, but it's very intuitive.
So far, I'm with you in the mechanics. So,
Okay.
but I'm not sure how this all gets into two qubits being highly correlated and entangled. But I like where
Yes.
you're headed so far.
Okay. Well, we're at the place where we can now describe how that happens. And again, I'm going to refer to this wonderful Penny Lane article. I also just love their hand-drawn graphics that we'll see in a second. So rather than reinventing the wheel, I'm going to just describe what they say.
Great.
So let's recap. Here's like a nice little treasure map. We want to start from two ions that are initialized, and we want to use the rules of the game, those three sort of cheat codes that we just described, to shine lasers on these ions such that the final state is this entangled state that we described earlier. Okay, so, or mathematically, I can express it like this. All right, so here's kind of the recipe or the rules that we follow to get from finish to from start to finish in the treasure map. So here's the idea. And I gotta say for the record, there are multiple ways that you could have done this, but this is just one example. So I think this is called a Sirac-Zoller gate. I hope I'm pronouncing that correctly. But this is one recipe that you could use to entangle two ions, but just think there are many others, but we're just focusing on one, okay? So step one, actually I should say step 0 that's not shown here. Initialize your two qubits so they're both in the ground state. How do you do that? Listen to like 2 episodes ago on this podcast. So we're going to write that as GG. So here are my two ions and they're both in gray. I think I was calling them A and B before, but Penny Lane is calling them 1 and 2. But look, there's also a 0 here. So what that means is that we also have to initialize the oscillation of our chain to be in its lowest energy level. And there are ways that you can do that too. So we talked a little bit about this a few episodes ago about cooling, kind of bringing things down to a still state so there's not so much kinetic energy. So step 0, initialize your qubits so that they're in the ground state and initialize the entire chain so that it's in the 0th energy state. Now, when you do that, step 1, apply that blue sideband transition on the first qubit. Okay, so remember what that means. That means it excites, right? It's the energy gap plus a little bit more. So it excites the first ion. So now it's in the excited state, and it bumps up the energy number of the harmonic oscillator from 0 to 1, right? That extra, you have extra in the bank. Okay, but it's in a superposition. What does that mean? Remember from our previous episode, I have an initial state, the ground state, and I have this new state called the first ion is excited. But look, by adjusting the duration of the laser pulse, you can put your two qubits in a superposition of the initialized state and this next one. So that's actually what they're doing. You just sort of shine your blue sideband transition laser for a certain time duration so that it's an even superposition of what we started with, the initialized state, that's GG0, and the result we get that we spoke about earlier. The first ion is excited and the energy of the whole oscillation chain has bumped up by 1. So you put them in a superposition by just shining it for a certain time duration. How's that so far?
Good. So that's just the first qubit that we're shooting
That's
at
right
now. Okay.
Just
gotcha.
the first qubit, just the first qubit. But now the second qubit is feeling left out, so we move to step 2. Now, for the second qubit, shine a laser such that its frequency exactly matches delta, the energy gap. So that's that carrier frequency. So if I do that, that means in my expression here, the second qubit, which was ground state in the first term of superposition and ground state in the second term, now they both turn to E's, okay? So we shine laser that exactly matched the energy gap. So G goes to E. Nothing too much there. How's that so far?
Okay, great.
That's great. Okay.
Yeah.
Finally, step 3 is you shine a laser on the second ion again. So we go first, second, second. First, second, second. But now, when you shine a laser on the second ion, you do the red sideband transition. So that's a laser whose frequency sort of is a little bit below the energy gap, right? So you have a deficiency in your bank. Okay, now what did we say? Let's think. Let's look at this second term on the left-hand side. You asked a good question. What if the energy level of your whole chain, the vibrational energy level, is 0? What happens? Nothing. We said nothing happens. 0 is like boring. So that's why this E, this second excited state, stays the same. But what happens if in this first term, your energy level is of the vibrational energy level is not 0? Well, it decreases by 1, right? You're sort of taking energy away from the chain. And then it turns out if your ion is excited, then that delta amount changes excited down to ground.
So you're reducing the energy in the chain,
Yes.
but you're also reducing the energy of the qubit
Yes.
from excited to ground.
Yes.
Okay.
You've de-excited the ion and you've de-excited the chain.
Okay.
So we just applied 3 laser pulses, 1 on the first ion, 1 on the second, another on the second. And that's it. We're done, okay? Because look at mathematically what the final state is. The final state is in an even superposition of I measure my first ion to be excited, the second ground, and the whole chain is at the 0th energy level. Or I measure the first ion to be ground, the second excited, and again, the whole chain is at the 0 energy level. So because in both terms, the whole chain is in the 0 energy level, it's kind of redundant. It's like, okay, just forget about that. Like, we know that already. So what are you left with? You're left with an even superposition of excited and ground or ground and excited, where even means 50-50. And that's even this mathematical expression is exactly what we said earlier. So we just created entanglement.
Okay. Yeah. Wow. I mean, I think I'm maybe a step behind you, but like that, I mean, I think I'm mostly picking up what you're dropping. The thing that is in my head right now is that last set of laser pulses, on the second qubit, brought that from an excited state into a ground state.
Yes.
At least that's what I think you mentioned.
That's what it says.
Yeah. Okay. So if that's the case, then how can it be measured as excited if the first qubit is ground, if we know that we moved the second qubit from excited to ground? Does that make sense? I thought our pulse specifically brought the second qubit from excited into ground. And now I think that what I'm seeing here is that, like, yes, that is kind of true, but also it could be excited if qubit 1 is measured in the ground state.
Yes. Okay. I see what you're saying. So let's look back at step 3. So here's step 3 again. I would say there's actually kind of 2 things we did in step 3. So remember, at step 3, our 2 ions are in a superposition of 2 possibilities. So either the whole chain can be in vibrational mode number 1, in which case the second ion is excited. Okay. Now, yes, if we apply the red sideband transition, then coming over here, you've de-excited that second ion and de-excited the chain. But there was another thing that could have happened, right? We were in a superposition initially. So the second scenario is the whole chain is at the 0th level, which is different now. And the second ion is excited. And remember, when the whole chain is at the 0 level, it stays excited. Nothing happens. Yeah.
Gotcha. Okay. Yeah. I kind of forgot that we're starting from a superposition state and we're not actually like measuring at that point. We're just adding more laser.
Exactly. Great question. Yes.
Okay.
Yes.
Thanks.
So now that you've done it, that's right. That is such a great point. Superposition is essential to creating entanglement. It's like you cannot have, they're inseparable. You need them.
Thanks for
mathematically.
going over that. Yeah, no, thanks for walking through that.
That's great. So at the end, you have a superposition. Like that's what entanglement is. You have a superposition of two possibilities. The first ion is excited, the second is ground, or the first ion is ground and the second is excited. And you have a 50-50 chance of measuring both. But the point is, if you measure, let's say, 50-50 chance, let's say the first one is excited. At that point, 100% of the time, the second ion will always be ground. So it's kind of like whatever probability or like who knows what's going to happen with the second ion, all of that uncertainty goes away as soon as you have measured the first ion. It's like, oh, thanks for clearing things up. Second ion, I now know what I'm doing. You know?
And you don't even have to measure the second one. You just know that the correlation is 100%. Yes. Is that okay?
Yes.
Wow.
So I think, okay, so that's the mechanics of entanglement. We have now described actually how to do this using lasers. And really it relies on the relationship between energy levels of an electron and how those energy levels leak over or borrow from the energy of the motion of the whole chain. That's how you create entanglement, which I think is really fascinating.
Yeah. Yeah, but it sounds like you have to do a lot of bookkeeping so that when you're designing these pulses, you have to kind of know what state the oscillation is in, what state each qubit is in, all of those things. Got to keep a lot of stuff straight in your mind.
Absolutely. It's a lot of math, but it can be done, as these very smart folks have described. I think, though, I understand a little bit better now why the adjective spooky and weird and non-intuitive is used, because it's interesting. We have been talking about two ions very close to each other on a chip, right? But the idea about entanglement, and I know we've talked about this before, is that your ion could be in outer space. And if I measure the first one as excited, the 100% of the time, the ion in outer space is always going to be ground. So I think that's where the interesting thing comes in, because how are they communicating then? If they're we can kind of say, oh yeah, if they're on a chip, something's probably going on, right? But what if they're not on a chip? What if they're way far apart? The idea behind entanglement. Yeah. Go ahead.
So you're saying that if you do this entanglement and then you go traveling, you take one of those ions and you move it someplace else, that entanglement stays in place.
Yeah.
And I think that's teleportation, or is that teleportation, or is that something?
It's related to else? Yes. Teleportation uses entanglement, and it uses this idea that you can Okay.
And so that definitely, felt spooky to me when I was first learning it, and honestly still is, the teleportation thing. But through this lens that you just described with entanglement, it kind of makes more sense, if I'm thinking about this right, that when you're entangling these ions, they do need to be close to each other. They have to be in a chain, At least that's what we're talking about right now. I'm curious if that's always true. So that when they're being prepared, they're near each other, and then they could be flying or
Yes.
separated or transported or
Yes.
something like that. But you can't
Yes.
entangle like two ions that are extremely far apart, like millions of miles or something, and just
Right.
like randomly take two ions, keep them apart, and then entangle them. You have to do some kind of
Yes.
preparation.
Yes, yes.
Is that
Yeah.
right?
I think that's right. They have
Okay.
to be close together, interact in some way to become entangled. And then they
Okay.
still possess the property even if they're far apart. But yeah.
Yeah. I mean, that feels less spooky to me because like you're preparing them together. So you're kind of setting things in motion. And then the distance maybe matters less because when you're measuring them, you're just measuring them. That has less of a, like of a distance thing to it. You're just shooting a laser at it and seeing if it fluoresces or not. But when you're doing this entanglement, like if the chain is really a big deal and part of it, then they have to be near each other when you're preparing that state. And then the state is set. At least this is my understanding of it from just from what you're saying,
Yeah.
just in this conversation, that the state is sort of set then, and then if you move them far apart from each other, they still were originally prepared together, and so their state is their state. And when you
Yeah.
measure one, you're gonna know something about the other one. You think?
Yeah.
Am I thinking about that right? I might be oversimplifying. I really don't know.
No, I think that's a great summary. That's a great summary. My only question would then be, after you've prepared them, suppose you do send one millions of miles away, and it, I measure my first ion and I find that it fluoresces. Then every time it fluoresces, the other one will not fluoresce. So how are they communicating at that point?
Well,
Like, you
I
see
mean,
what I'm saying? They're not in the
Yeah.
chain anymore. So they don't have the
Yeah.
vibrational bank to pull from anymore because
Oh,
they're not
yeah.
near it.
Yeah.
So,
Yeah. I mean, yeah, I feel like that they're not actually communicating, but I think we're definitely getting out of my depth here. But I feel like that the communication happened during the preparation stage, and then there no more
yes.
communication needs to happen. So any kind of absorption, of extra energy from the chain, like the bank is
Those happen.
closed at
Yes.
that point, and then you can move them around. And the only thing that's going to matter is like decoherence issues, like interference from the outside world would then mess with that energy state, and the entanglement I would guess could degrade if you send that electron through some kind of wire or something, and it gets interfered with the outside world. Then it's not going to be entangled anymore. But I feel like that all the communication happened during the preparation phase, as you're describing it, at least. And so they're not really communicating with each other millions of miles away. Like the communication happened back in the origin story of the entanglement, and then you're just like, doing measurements. So you're just like seeing
Yes.
what's happening. At least
Yes.
that's my immediate interpretation. But lots of big asterisks near that, since I am not a quantum physicist.
Yeah. Well, I'm not either, but I can appreciate, I think, a little bit better the conversation surrounding it. And for me personally, thinking about it concretely does help demystify it and maybe gives me a better vantage point to think about it a little bit more deeply. So I hope it wasn't too
Yeah.
confusing. How was that?
No, it was great. Like I was waiting for like more. Like I thought that I didn't know we were done, Tai-Danae.
Yeah.
Like I mean, I think that this is making me think I need to go back and watch one of our season 1 conversations with
Yes.
Adam Lewis, because I think that we had something about entanglement then,
Yeah.
and there was a lot of philosophical talk there that I think was really
Right.
interesting. But I
Yes.
do kind of remember him doing some stuff with sticky notes and colors, and I
Yes.
think that's going to probably make more sense to me now. So I think I
Yeah.
need to go back and check that one out.
Yes. Yes.
So yeah, I mean, that seems like I think you did it. Like that thing that I was hoping for in the beginning with to do with entanglement, like you did with superposition. It just seems like it's just another series of laser pulses at the right secret frequencies, and get that
Yes.
cheat code in, and then you've done it. So that
Yes.
seems like, I'm going to say, for me, at least relatively straightforward, at least as you've explained it. I have so many questions about the like, so what? Like, great. So we've got something
Yeah.
entangled. Like, what does that actually give us? But that might be
Yeah.
outside the scope of this conversation.
Yeah.
But it seems like that there is something important, very important about entanglement and quantum computing.
Yeah.
Is that right?
Yes.
Okay.
Okay.
Makes me think that's a pin for another conversation with how you
Another
answered that
time.
question. Is that
Yeah.
right?
Yeah,
Okay.
that's right. I
Fair
have
enough.
ideas about that, but it's just interesting when you kind of when you look for applications of entanglement, online or something. It's kind of hard to get a straightforward answer, which is
Mm.
interesting because it's, you know, such a big deal, or folks make such a big deal out of it. So that's something that I want to understand a little bit better. Sure, it's used in quantum computing. Okay, but then, there's like debates. Is it really entanglement that helps, give quantum computers an advantage over classical? There's like people that say yes or no, and there's papers written about that. What are other ways in which entanglement is useful? Okay, quantum information like teleportation, is that used in the quantum internet? Well, we don't have a quantum internet yet, but like that's an idea in theory. But how exactly would that be used? These are things I don't understand very well yet, but I'm on a mission, so maybe we'll come back another day and chat.
Yeah, no, I'm right there with you. So yeah, maybe now I can talk a little bit about, like, we usually have a little superconducting quantum computer corner.
Yes, yes.
And I can talk a little bit about how this works in superconducting quantum computers. But actually, even before we get to that, maybe I'll do like a little summary recap of where we are in DiVincenzo's criteria with trapped ion quantum
Great.
computers. Does that sound all right?
Yes, yes,
Okay.
let's do it.
All right. I'm going to refer to some of my notes here. So, the first criterion is a well-characterized and scalable qubit, and we have an episode or a conversation on that. And it's mostly met with trapped ion quantum computers. We've known about these types of ions for a very long time, and their behavior is very well documented. But the scalable part is kind of tough. And I think I remember reading that once you get over 100 qubits or so in that pearl necklace, that sort of chain, that it starts to get kind of hard to control them. And especially with this harmonic oscillation that you were just talking about, which now makes a lot more sense to me. Once your chain gets really, really long, it's a lot harder to sort of manage that oscillation.
Yeah.
So there's some technological limits there that engineers are still working on. With second criterion around qubit initialization, this is kind of easy for trapped ions with optical pumping technology. It's pretty easy for folks to be able to know what the right frequency of laser is to shoot at the ion to get it into its initialization state, and to do that kind of cycling to really get it into its ground state that we talked about a couple of conversations ago. And then with criterion 3, long coherence times, we didn't talk about that too much today, but I know that two-qubit gates they take longer to set up. You're doing all this extra shooting of lasers. You talked about like 3 different steps, and each one of those steps can be more than just one laser pulse. I think I remember with getting ions into superposition, it was several laser pulses that needed to happen. And I'm guessing that's probably similar to going through those steps that you talked about today. So it's just more time that's needed in order to get 2-qubit gates set up. And so decoherence times play an even bigger role. That if it takes longer to get through a gate, then you have less time before your ions decohere, and then you have to start over again with initialization. So that's starting to become a bigger problem with trapped ions. So something that still needs to be kind of worked on. And these the criterion 4 is a set of universal gates. And I think we've talked about that. And it seems like you got the treasure map. It's pretty simple to get 2-qubit gates going. And certainly with single qubit gates, like no problem. I think it's just decoherence times, again, that kind of get into here, that you can know which cheat code to put into the system in order to get your 2-qubit gate to work. But that's going to take a long time or longer time. And so your decoherence countdown sort of becomes a bigger issue. So those are the criteria that we've talked about so far. And then we have a fifth one coming up, I think, in our next conversation, where we'll start to really get into measurement of individual qubits. Like, how do we get that readout at the end? So that'll be a fun one to talk about next time.
Yeah, excellent. I'm looking forward to that. But before we wrap up, Any thoughts on the superconducting side of things?
Right. Thank you. So yes, I'm definitely going to refer to my notes here. So I did some reading and there's another Penny Lane article. I know we're just using that site a lot.
Yeah.
It's great.
It's
So
great.
we'll put that into the description. And essentially, from what I understand, there are a couple of different ways. Just like how you mentioned with trapped ions, there's a few different paths that you can take in that treasure map. There's a couple of different like infrastructural ways to be able to execute 2-qubit gates in superconducting quantum computers. One of them is called capacitive coupling, and that's where you take 2 qubits, 2 artificial atoms, and from what I understand, you actually connect them together with a superconducting wire and a capacitor. And you're sort of physically connecting them together. And there's a lot of buzzwords out there around what that's called or what sort of techniques are used. And if you do some reading about this, you'll hear about squids, which are superconducting interference devices. I think that's quantum or superconducting quantum interference devices. I think that's what SQUID stands for, if I remember correctly. And you can make these things called flux tunable qubits. And that lets you sort of manipulate the energy of each qubit in a very specific way, and that can help you to entangle qubits and create two qubit gates. There's another way that's a lot more similar to what you just talked about in trapped ion quantum computers, and that's called an all-microwave solution. And that's essentially where you can put 2 qubits really close together in the same, what they call a cavity in a superconducting quantum computer. And then just like how you're using lasers with the, I think you were calling like the delta plus and delta minus, or like the red sideband and the blue sideband, I think. Very similarly, you can use microwaves of different frequencies to entangle those 2 qubits together and create these 2-qubit gates. So this is like definitely out of my wheelhouse a little bit, but that's what the research that I've done, and we'll link that article down below. And I think even if I just go back and read that again after the explanation that you just gave me, I think it'll make a lot more sense to me and hopefully anybody who's tracking this conversation.
Yeah, excellent. Okay, good. I'll have to take a look at that article too. All right. I guess that sort of concludes today's conversation. And next time we'll get to the final criterion on DiVincenzo's list.
Yeah, measurement, which I know you've talked about this a lot with, like it's a blob of fluorescence or it's not, and all of those things. So it'll be nice to dig into that a little bit. So yeah, I'm looking forward to that one too.
Great. See you next time.
See you then. Bye.